Yes, on this computer. Okay, so it's recording. All right, let's get back to screen sharing. Share the whole desktop. Bingo. Make a chat window. All right. Looks good enough. Let's go. Guess we don't need that. Oh. Plop. Plop. All right. So one thing I wanted to mention, because people do it every year, and that's when they're building their values, and this for assignment 1, when you're building your int set value, often you might build some data structure which you create by palloc, and you turn mute, please. I'll mute everybody all at once. Doesn't look like it. Thanks. All right. Yeah, so when you're building your value, your int set value, sometimes you'll build some kind of in-memory data structure, and you'll set up a pointer to this data structure, and you might return the value as a pointer to this data structure. And don't say, why would I do that? Because I've seen this done many times. All right, so this thing that you've built contains a pointer. A copy of it goes into a memory buffer, and eventually the memory buffer gets written to disk. So this value, this pointer value, goes there and goes there. The system won't crash at this point. That's fine. Maybe I should turn my lights on. But when you come to try and do a select, you're going to read this object back, store it into a memory buffer. Eventually, to display it, you'll probably end up loading the value into working memory. It contains a pointer. The pointer was relevant back in this process, but is no longer relevant in this process. And what's going to happen? Server will probably crash. If it doesn't crash, it might be that this is pointing to some piece of memory that was allocated at some point and might contain rubbish values. Either way, it doesn't work. You can't store a pointer in the database, a pointer that was created at some point in working memory. Yeah, you're right, Curtis. If you're lucky, it'll crash. Otherwise, it'll just give you rubbish stuff. So you can't store a pointer into the disk and expect it to work when you read it back, because the whole process working memory is totally different, because it's quite possibly a different process, a different user, someone coming along trying to access the int set that you created, and whatever the pointer was, it's no longer valid. So just be careful of that. So build your datum correctly. If you have to create some kind of structure, that structure will need to be incorporated into your datum, which will then go into the memory buffer and then go to disk. And when you get this value back, you'll have all of the information that was in here available to you. All right, so whoever's not mute, please mute. By datum, do you mean the struct that we make to some extent, that's what I mean, but it's more the wrapper around the structure that you make for your internal representation. So your internal rep will be a bunch of memory, bytes, and should ultimately have a header at the front. But the whole datum has to be a single object that was malloced in its entirety. So basically what I'm saying is if you want to malloc stuff and it's not incorporated into your datum, it's not going to work. I'm sure there are examples of doing variable length datum in the tutorial folder or in that contrib folder. Go and have a look. If someone knows where the doc, yeah, stop bragging. Is it mentioned in the documentation somewhere? Yeah. But that's part of the deal with this assignment. You have to figure out how to do that, but I'm sure there are examples somewhere in the Postgres source code. Even, I mean, the implementation of varchar ought to be in there somewhere in the source code. So if you want to go and look there, or you can look at create type. What a good idea. All right. Yeah, so don't make that mistake. And if someone asks a question, of course, there's not that many people here. I don't think. How many? 40. All right. If someone other than the 40 people who are here does that and asks a question on the forum, I'll simply point them back to this slide and say, this is what you did. All right. Any other questions on the assignment? Please mute yourself. I can't work out how to mute everybody. If I could, I would. What's that? Mute. Wait, how does one actually make a datum a pointer? I can't remember off the top of my head, but you make it as PD or pointer something. It's not going to cause a problem as long as it's correctly incorporated into the datum. So you need to work out what's the appropriate header for your object and make sure that your datum isn't typed PG underscore pointer something, capital, all caps. I suppose I could go and have a look. Let's see. Oh, I'll cry. Probably not where I want to be. Oh, it's a long way down. Where am I? Oh, gosh, it is a long way down. I know, that's where I wanted to be. Source/tutorial. There could well be examples in here of making pointers. complex.c obviously does it the right way. Interesting. All right, so I would have thought this is the kind of thing that's going to cause problems. So you need to have a look at what the macros for doing this are. Make sure you use the right one. Look in the last line of complex in, that's what I'm looking at. What was it? What? Love that auto correction. And the true. That would also be a problem. Right, so it's not just the datum containing a pointer to somewhere in memory, but even if you incorporate, let's say, the top level of your data structure into the datum, yes, if you put an array in the struct, well, this is what I was just about to say. If you put an array into the struct and all it contains is values, not pointers, then it'll be fine. But if your array contains pointers, then they will also be stored kind of like this, and when they come back, they won't be valid either. Same thing, int star, int square brackets, same thing. To some extent. Yeah, maybe. All right, keep an eye on the chat. All right, let's have a look at some exercises. All right, so now what we're interested in is talking about different file structures and how they behave when we are modifying the files. So far we've said a lot about what happens when you do a query.
Version.
But mute, please. Do you understand the meaning of the word mute? Because you're not mute. Sounds better. All right. So what we're talking about a file. Let's just maybe. Actually, I might wake up a quick diagram because it's probably easier to see what's going on. Let's just grab a rectangle. Probably need to make that text a bit bigger, don't I? I know what to do. Make that whole thing bigger. All right. Extend. Okay, so here's our data file, and there are some indeterminate number of pages in between. All right, so according to the question, the header tells us how many total number of tuples, average size of a tuple, total number of pages, size of each page, and the capacity. All right, now. And also the header page might contain a page ID to the first page with free space. And that page may contain a link to another page with free space, and so on. All right, so we want to insert a new tuple. Let's make a small one. So the other assumption that we're making here when we're computing the cost is that we would typically cache this header page in memory. Right, so I'm going to assume we've got this, and then what the one way the file system or the database system might do an insertion is it could go and look here and see which page has some free space. If we were really smart, what we'd actually put here is how much free space each page has, or pages with free space also how much. But let's assume that we didn't do that. So what we do, we read the page which contains the first chunk of free space, and then we check, is there room in this page for the tuple? If there is, so let's say this happens to be the first page with free space, and there's room to store that tuple in there. So we'd insert the tuple, and then we'd write this page back out. The other thing we need to do at this point is, because this contains information about number of tuples, number of pages, etc., clearly this is about to change. So we've made changes to this as well because we added one more tuple to the file, so we end up writing this page out. So the actual cost, assuming that we've got this cached somewhere when we open the file or open this relation, say, the cost is going to be the cost to read the first data page. Oh yeah, the other thing too, if the free list header or the free list pointer points us to a page that doesn't have space for the tuple, then we start chaining along the free list pointers looking for a page that does, and maybe there's space in the last page. Or if there's not enough space in any of the pages with free space, then we could add a new data page, insert the tuple as the first and only tuple in that page, and then write it out. So what does it cost? Now let's, all right, we don't have to read the header because we assume it's already there. And we have to have a look at least one page to see whether there's free space. So there's going to be one data read, but in fact, we don't know how many we have to read. In fact, the way this algorithm is written, it does a first check. So if this page was didn't have enough space, it would simply add a new page at the end of the file and put the tuple there. So if we're following this algorithm, then there's going to be one read of a data page, and then there's going to be one write of a data page once we insert the tuple. Now this will be true whether it's whether we insert the tuple into an existing page or whether we have to add a new page on the end and insert the tuple there. So we're going to write out one data page either way. And then we're going to have to write out a header page. So there's going to be one data page read one data page right, and we have to write the header because we inserted a new tuple and therefore changed some of the values in the header. So they need to be updated. So that's according to what we've got here. If we did it the way I described before, where let's say this page has some free space, is the free space enough to hold this tuple? Maybe not. And then it links to a later data page. Is there enough free space here to hold this tuple? Maybe not. Then we link to another data page. Is there enough free space to hold this tuple? If there is, we can insert it. If there's not, we need to add new page on the end. And clearly that new page is going to become part of the free list. So the cost would be a little bit different then, of course. So it's not clear how many data pages we're going to have to read. That depends on the distribution of free space within the data pages and the size of this tuple. But ultimately, we end up writing out a single data page. This is always the case. And we write out the header file because we inserted a new tuple. All right, so how many data pages do we have to look at? Well, basically the length of the free list. And who knows how long that is. I mean, a lot of the time, if a file has been around for a while and it's had insertions and deletions, it's quite possible that every data page will have some free space in it. So the worst case would be that we need to read all of the data pages. The best case, of course, is, let's say this is the first page in the free list. We go there and there's space for this tuple. So maybe let me call that X, and X is a value in the range 1 up to B. Okay, so that's a really simple file structure. There's nothing inherently ordered or hashed or anything about it. It's simply a collection of data pages, a sequence of data pages, which have some number of tuples. Some of the data pages may have free space. And the free space may or may not be large enough to hold our new tuple. Okay, what about deletion? Well, this depends a little bit. If we're deleting based on a primary key, so we say delete from students where ID equals 1, 2, 3, 4, 5, 6, and we'll assume that only matches one tuple. So what we have to do, start from the start, and since this is a heap file, there's no inherent ordering or any other way to find the match. So we look in here, is the tuple here? Nope. Look in here, is the tuple here? Nope. Keep looking, and eventually we find the tuple up here, say. So then we remove the tuple from the page and flag the fact that we have one less tuple. So removing the tuple from the page could just involve putting an entry in the directory to say this slot is no longer used. We haven't really said much about the internal page structure, but what we're really interested in here. So to do this, the best case, clearly the tuple we want happens to be in the first page. So once again, we assume that the header page is cached, so we don't have to read it. Plus, one data page read plus one data page write. Interesting question. Plus one header write. In the worst case, obviously, oops. Is where we have to scan all of the data pages to find the one that contains the tuple that we're deleting. Now, a couple of other things to consider here. When we delete the tuple, this page now has at least some free space. If it had free space before, then okay, that's fine. Oh, by the way, the reason we need to write the header is we've got one less tuple that we had before, so that has to be reflected here. Yeah, if the data page that we removed the tuple from had free space, that's fine, it's still sitting in the free list. If it didn't have free space before, now it does, and what we could do is say, all right, this, let's say we remove the tuple from this page, this could now become the head of the free list, and it could reference the page that was at the head of the free list in the header page. So that would involve no extra reads and writes. Okay, so all we're doing is modifying this page, which we would have done anyway to remove the tuple, and we're modifying this page to change the free list, but we were modifying this page anyway to change the number of tuples. So let's imagine, I need more pages really to make an interesting free list, but there you go. I need to get my drawing tool back to the middle of the screen and stick a arrow there. And then this page could have a link to some other page that already has free space in it. So let's say, for the sake of argument, that this is another page with free space. Oh, let's try and make that a bit. Yeah, looks slightly better. Okay, I'll have to save all these graphics. Okay, so what we've got here, we've got the header page, contains the page ID. I've written them as pointers, but they're actually indexes to the first data page that we know has free space. Then that data page has, doesn't want to look nice, has the index of the next page with free space. Okay, so that's the kind of structure we might have in this scenario. If we didn't want to manage this free list at all, then it wouldn't actually change the cost, because we'd still have to scan data pages until we find the place to remove the data tuple from. We'd remove the tuple, we'd write out the data page, and we'd write out the header page. So it wouldn't actually change the cost here, even if we didn't have a free list. All right. So what do we do if there are multiple matching tuples? You got actual cost, same, yeah, all right, true. It's all ought to be. allowing for the worst case. Right, if we got multiple matches, the best case, all right, yeah. So what do we do? So we've got effectively got a query. Let's change that to, it's not nice, is it? So now we've got a query which can match multiple tuples. So we look at the first data page. Are there any matches in here? No. Are there any matches in here? Yes. Are there any matches in here? No. ... Are there any matches in here? No. Perhaps. So the first thing, we definitely have to read all of the data pages because we don't have an index, we don't have any other way of establishing whether there are any tuples that match the query in any particular data page apart from reading the page and scanning it. All right, now if we only find one tuple that matches the query, then the cost goes back to the cost in this scenario. So B reads and 2 writes in the worst case. In fact, it's always going to be this cost because we always have to read everything. All right, now one of those writes here was writing a modified data page. It's possible that every page we go to has some tuples that match this query. So every one of those pages we're going to read in, we're going to make changes to it, and we're going to write it out. So, where'd that go? There. So we could end up having to write B data pages. And of course, we got to write the header page because we need to keep track of how many records there are in the file. Now, I've mentioned a quantity before, B sub Q, which is we're going to use to talk about the number of pages that actually contain matching tuples. And this depends on the query, depends on the distribution of data values. You know, if we are asked to delete all the students who are over 40, for example, that'd be mean, wouldn't it? And there aren't many students over 40, then not many tuples would end up being deleted. And here we're assuming, once again, there's no ordering on the tuples, so the 40-year-olds could be distributed, you know, throughout the data pages. Or all of the 40-year-olds might, by coincidence, appear on a single data page, in which case BQ would be 1. So in the general case, we can say, yes, we have to read all of the pages in the data file to find matching tuples. And I guess just basically this is going to happen whenever we ask a query on a not unique attribute. And the most obvious example is if we ask not on a primary key. All right, so we read all the pages, we write out as many as contained matching tuples. Even if a page contains 10 matching tuples, doesn't affect the number of writes. We simply run through that page. Every time we find a matching tuple, we change the internals of the page to reflect that. And once we've looked at all of the tuples in the page, then we write it out. And we've also got a write of the header page. All right, so that's a heap file, relatively straightforward. Imagine that the file contains sorted data. So now we probably won't have free lists because there's an external way of determining which page a tuple belongs in. What happened to my tuple? It went away. Come back, tuple. There you are. Oh, stupid. Sometimes I hate OmniGraffle. Let me try that again. This time, don't make it too small. Right, that'll do. Okay, so now we've got a tuple that we're trying to insert. We know that all of the data in here is, well, this depends, once again, depends on whether we're talking a unique attribute or a non-unique attribute. If we're talking unique attribute, like a primary key, all of the key values in here are less than all of the key values in here, are less than all of the key values, and this contains all of the largest key values. Now, within the data page, the tuples don't have to be ordered, and it doesn't really cost, what? There's a, yeah, it probably was, doesn't matter. The tuples don't have to be ordered because it's not really going to cost us any more. We have to read the data page anyway, and discovering the location of a tuple within the data page is all in-memory stuff. All right, so first thing is that we can now do a binary search to find the relevant page. So let's assume that we're inserting a tuple based on its primary key. All right, I probably should have added a few more data pages. Doesn't matter. So hopefully we all know what binary search is. You start at the middle. If the key value in the tuple is smaller than all of the key values in this data page, then we look to the earlier part of the file. If the key value here, and I guess this is something that's slightly different to, you know, an ordinary binary search in an array, which you've probably seen in your data structures course, but we have to look for the maximum key value in the page, and if the tuple is the key value in the tuple is larger than that, then we go towards the top end of the file. Also, we've got to find the smallest key value in the page. If the key value in the tuple is less than that, then we go in this direction. Now, of course, that suggests that maybe it might be useful to put in the page the minimum and maximum key values. So we could put a header, or put as part of the header the min and max key values, which would make that test reasonably straightforward, although it doesn't, of course, does not save any reading and writing costs. But it would save us scanning through the page. All right. So we've used our binary search to find the appropriate page. If there's room in the page, no problem. We stick the tuple in here. And so we need to write the data page out. We need to write the header page out. And of course, how many pages do we have to read in order to find the appropriate page to insert the tuple? It's binary search, so log2b. Right, now this is where things get a little bit different to the insertions that we were doing before. That if there's not room in the page, we can't say, all right, I'll put it in the next page, because the value might not be great, the key value might not be greater than the largest key value in this page. So in this scenario, what we're likely to do is to add an overflow page. And so imagine this page is full, so we make an overflow page. Whoa, that was interesting. Let me just send to the back so our tuple appears. So we might end up having to possibly create a new overflow page. All right, so what's the deal there with page reads and page writes? All right, we've already got a log2b, that's fine. If the tuple fits, then we can put it there and write out that single page. If it doesn't fit, we have to create an overflow page, which of course we'd initially do in memory. We'd insert a tuple into it, and then we'd write that page to disk. But we'd also need to write this page to disk because we modified this page by adding a pointer to an overflow page. So we'd end up doing 2 data page writes in this scenario. And of course, we've updated the header because we added a new tuple. So the thing that changed is the search to find the place where the tuple belongs. If you don't have overflow pages, then the only solution to this issue is to start pushing tuples up the file. So if you, let's say we don't have this page, let me just take that away. So this page doesn't exist. So we insist on putting the tuple in here, but there's no room. So we have to make room. And the only way we can make room is to take the tuple with the largest key value and push it to the next page. Now, if we're lucky, the next page has enough room for that tuple. So we simply move that tuple to another page and we end up writing. In fact, we wouldn't even change this page. We'd just end up writing out the other data page, the one we pushed it into. Of course, if there was no room in this data page, then we'd have to repeat the process. Well, this tuple would go into this page. Sorry, this isn't our original tuple. Whoops, that ended up there. So what we ended up doing was taking the maximum tuple from this page and moving it up to here. If there was room in this page, oh, and one thing we're sure, since the file's sorted and assuming that we're dealing with primary keys, is that all of the tuples in this page are larger than this one. So we'd repeat the same kind of process. If this doesn't fit, then we take the largest tuple from this page, push it up to the next page, and so on. All right, so that can end up being quite expensive and having to rewrite a large chunk of the file, which is a good reason why we'd want to have overflow pages, even though that involves maintaining a separate file. It certainly makes insertion potentially easier. All right, so down here, blah, blah, blah. So we're still doing the same number of reads to find the appropriate data page where the new tuple belongs. But then we may have a whole bunch of reads and writes to push tuples up until we find a page with room. So you can have a look at the best case and the worst case and so on. This best case here actually not only new tuple in the last page, but also, I mean, these values here kind of assume so that would be the scenario. These would be the values in there. For some other cases, like I said before, we try to insert the tuple, there's no room, so we have to take the maximum tuple and push it up, and maybe there's room in the following page, so that can just go straight there. So there'd only be one page right, 2 page writes. We have to write this one out because it's got a new tuple in, and we have to write this page out because it's got a new tuple in. This tuple was deleted from there to make room for that. Probably should distinguish those tuples, shouldn't I? Yeah. Thought about giving this one a name. Probably should have. I was actually going to call it tuple max to indicate that it was the tuple that had the largest key value in here. So that's the one that might get booted out to the next page. All right, so deleting from a sorted file. Okay, so let's, for the sake of argument here, just assume we're dealing with a deletion that's specified by a primary key. So let's assume we have a student who cheated on the exam and is therefore going to be removed from...
周四的课都是只讲1小时。
Mute, please. All right, so if we're doing this deletion, then what we've got to do is find a page that contains this guy. All right, so to do that, once again, that's a binary search. So that's log 2b pages that we need to look at. Oh, actually, that's log 2b data pages. If we actually got overflow pages, then you'd need to look at as many of them that are attached to the pages that you hit during your binary search. So there may be more than log 2b. All right, well, let's assume that at this point we don't have overflow pages, so we just got that. All right. So then we find this student, we remove their record, and we have to write out the data page that used to contain them. So this is all reads plus 1. So we got those two, and I think that's pretty much it. I can't think of any other weird
这个 P
scenario.
真的好喜欢吸鼻子。
Mute.
Oh, sorry.
Thank you. All right. I guess, all right, if we want to talk about being ageist, let's say we want to get rid of all the old students. All right, well, what we do is we do a binary search based on this value to find the first page containing students whose age was 50, or maybe we could search for 51. And then from that point on, we need to delete all of the tuples that are in the file. Now, where is this page? Could be anywhere. You know, if we used 60, then we're probably not going to find many students that old. So maybe all of the 60-plus-year-olds are in the last page. So all we'd have to do then is go through this page and find all of the tuples containing age greater than or equal to 60 and delete those tuples. But if, like I said, if it was something like greater than or equal to 40, then we'd search for 40, we might find it in this page, and then we'd have to delete all of the tuples in subsequent pages. And I guess if you really wanted to clean up, you could remove all of the data pages beyond this point and modify that. And obviously you're going to modify R because you've got way less tuples than you started with. Now, of course, if it turned out that, you know, the first 40-year-old was here, there's no guarantee that there won't be 39-year-olds and 38-year-olds in this page. So we need to do a scan of this page just to make sure that we're not deleting tuples that don't satisfy this criteria. But certainly a binary search will enable us to find this page in the first place. Right, so in this scenario, so this we're talking about and of course, we're assuming that the attribute we're deleting on is the sorting key. So we still do log2 b reads using the bottom bound. No, you can apply the same thing to less than or equal to 18 or something. But the number of page reads is kind of, it would be something like that. Now this assumes that we're going to actually keep all those pages in the file as empty pages, but it's really as many pages as there are matching tuples need to be written, and then update the header as well. Right, so that would be the scenario there. Right, what about inserting into a hashed file? Okay, so let's delete that. So we take our tuple, we run it through our hash function. So the hash of tuple 1 tells us which page tuple 1 belongs in. So imagine that was 1. coincidence for tuple 1. So if these pages are indexed by probably should have had these index values before, doesn't matter. Okay, so if the hash value, now you might say, hey, wait a minute, what about the header page? True, all right? If that really was a page at the start of this file, and there's nothing that says it couldn't be a page in a separate file, but if it was, then of course these indexes would change to 1, 2, up to B. All right, anyway, so h11 is x, let's say x equals 1, so therefore the tuple has to go, or has to be associated with this page, this data page. What if this data page is full? The standard strategy is to make an overflow page and put the tuple in there. And, you know, it's possible that the overflow page already exists, in which case you look here and say, that's full, there's an overflow page. So I go and look at the overflow page. What if that one's full? Then we'd add another overflow page onto this. And all right, so that's full, that's full. This data page isn't full. So the tuple has vanished until we push that page to the back. And so we can end up with these overflow chains. Now, whether we end up with overflow chains is a little bit dependent on the total number of pages that we have at the first level. Why delete based on this log2 reads? No, it's log2 reads because we have to search to find the first page containing that's a nice little spell correction, attractions, attributes, yeah. So we need log2b reads to find the first page containing the containing the first tuple that matches the thing. So I'll put back, so the whole point of this was delete from students where page let's move this away. Right, so we need to find which data pages in the file need to be cleaned out. To do that, remember here we're assuming that this is the sort key, so the student records are sorted by age. So we need to find a page that contains the tuple with the smallest value that satisfies this condition. Right, now if you want to make the assumption that there's always going to be a 40-year-old, at least one of them, or that every age is represented in the data file, then you simply do a binary search for this value here. And that will find you a page in the data file. Once again, forget about the overflow pages, which may exist, but it'll find you the first tuple or the first page in the data file that contains tuples satisfying this condition, and then since the file is sorted on age, then we delete all the subsequent tuples. But the point is that we're effectively doing something that looks like that. And the way we would have done this is to do a binary search on that condition there. All right, so that's where the log2b comes from. We got to find the starting point and then delete stuff after that. Of course, you know, if it was, if we're deleting everything less than or equal to 40, then we'd still do a search for 40 and then delete things before that. But the search for 40 is log2b. What if there were no students age 40? Well, the binary search is going to find a page where we may have students whose ages range from 35 to 45, but there happens to be none that equal 40. We're still going to find that page, and then we can start looking through the page, searching for tuples that satisfy that particular condition. So whatever, it's going to be a log2b search. All right, getting back to hashing. We assume that's very cheap. So we're going back to here. Hash functions have to be designed so they don't cost a lot. In fact, let's get rid of that. And let's say the hash value of tuple 1 happens to be 1. All right. That tells us that tuple 1 needs to be associated with this data page here. Now, if we're lucky, that page has space in it, and we can insert the tuple straight away. And so we need to read that, and we need to write it out. So the best case scenario is 0. So once again, we assume that we already had the header page. 0 header page reads plus. Okay, so hashing makes it really inexpensive to do this. When it works ideally. So tuple 1 gets inserted into here. The only thing we need to do is read this page, because that's where tuple 1 belongs. Insert the tuple, write the page out, and update the header page because we added one tuple. So that, oh no, I've ended up with a duplicate. Didn't notice that down there. So that's the best case scenario. Come back, you. In a not so optimal case, we may need to read some pages in an overflow chain. Now, depending on how you structure your overflow chains, it's possible that they're always going to be full except for the last page in the overflow chain. So if you knew that, then potentially you could jump straight from this page to the end of the overflow chain. But if you didn't know that, you'd have to say, all right, tuple 1 doesn't fit there. Does it fit here? Well, it's possible that there may be some space because there was a tuple there that's been deleted. Maybe there isn't enough space for tuple 1. And when I say not enough space, this depends on how large tuple 1 is as well. There may be space, but it's not big enough to hold that particular tuple. Right, doesn't fit there. Does it fit here? Yes. So we insert the tuple into that page. So to get to that point, we had to read the data page, read the first page in the overflow chain, read the second page in the overflow chain, and assuming we're not adding any new pages, then the only page we need to write out is this one. And then we need to update the header page, of course, because we added a tuple. So what's the worst case that can happen there? I'll shorten that. And then how many pages do we need to read here? And in the worst case is where we pick the page that has the longest overflow chain, and we have to go right to the end of the overflow chain. Okay, let's try and neaten that up a bit. All right. So, yeah, so the worst case scenario is where we end up scanning along overflow chain. Why would an overflow chain be long? Well, maybe we've chosen a crappy hash function and it always hashes to the value 1. In that case, all of these data pages would be empty and everything would be hanging off this overflow chain. Or maybe the distribution of key values, so we're using the key value of tuple 1 to do this, so maybe this would have been a slightly more accurate thing to say. You stupid magic mouse. All right. Stop it. Yeah, so if the distribution of key values is not uniform, then the distribution of hash values is not uniform, and the number of tuples that go into particular pages won't be uniform as well. So some data pages may have no overflows and some data pages may have extra overflows. Now, of course, this raises the issue, thank you, how many pages should we have? And that, if you knew in advance the likely number of records, you could decide that you wanted enough pages that you could, if you ended up having enough records to fill those pages. So basically, you choose the number of pages, total number of records divided by the capacity of each page. So you could do that, but if you ended up with more data, then inevitably you're going to end up with overflow chains. If you choose too few pages, well, yes, sure, you're going to get overflow chains up front. So an interesting question. What can we do about this? It would be nice if we could expand or contract the size of the hash file to cope with significant changes in the number of tuples being stored. And bingo, there are techniques for doing that, and we'll talk about them later. All right, deleting from a hash function, well, that depends on how you try to do the deletion. If your deletion looks like this, once again, we're talking about the naughty student. So there, basically, every time you do a deletion, you've got a where clause, which indicates some tuples that need to be deleted. In this case, equality on a primary key indicates one tuple to be deleted. So the basic first step is to find that tuple. And to find that tuple, we're going to apply our hash function to the key value. And that'll give us some page, so all right, leave it as 1. So to delete this student is associated with page 1. Page 1 has overflow pages, so then we need to check all of the data pages in the overflow chain to see where that particular student is. So maybe they're in this data page, maybe they're in this, or maybe they're in this. So in the best case scenario, the student that we're trying to delete happens to be in this page, and we got to that page simply by looking at the hash value, so that would be 1 page read and 1 page write once we deleted the student, plus 1 deletion from the header page. So that's pretty much the same as that. Actually, I'll go back and look at that in a moment because I missed a case. All right, worst case scenario is that we pick the data page with the longest overflow chain, and the tuple we're deleting is right at the end of that overflow chain. So it looks a little bit similar to this one. In fact, it's very similar to that one. Now that assumes that we don't care about compressing these overflow chains. If we are worried about that, then maybe if we delete enough tuples from an overflow chain, we might want to push some of the tuples down and then delete the data page at the end of the overflow chain, for example. So that would involve more page writes. Okay, now I did miss a case when we were doing the insertion into values. All right, and then whatever the other attributes are. Okay, so if we're inserting this new tuple in, the one case that I missed was the case where, let's remove that temporarily. So there's only a single overflow page. So we try to insert this tuple here, that's full. Go to the overflow page, that's also full. So we need to add a new page in the overflow chain. Insert the tuple into that page, and obviously we write that page out, but we also need to write this page because we added a pointer to an overflow page. We didn't change the data, but we did change some of the metadata in that page. So all these things that I've written as pointers, I should make them look like pointers. Let me just do that. There will most likely be page IDs page offsets into an overflow file that happen to be stored somewhere in the header for each of these data pages. So, it's kind of, is there an overflow page? Here's where you'll find it in the overflow file, that kind of thing. All right. So what would the impact of that be on this? In fact, it would make the worst case scenario 2 data page writes rather than just 1. So we'd have to, all right, we create a new data page, stick a new tuple into it, write it out. That's kind of obvious, but we also have to change the overflow pointer in this page and write that page out. So that would be the worst case scenario. All right. So you can sit there and you can analyze the way things are happening, and you can come up with formulae that describe how many page reads and how many page writes are occurring for these kind of operations. We don't normally talk about the cost of insertion and deletion, but it is relatively important to take into account, and especially if we are doing lots of updates on the file, because sometimes these operations can potentially be non-trivial cost. And indexing is a particular instance of that, where indexing, adding an index to a file makes it faster to search, clearly, but makes the update for tuples in that table that has the index almost twice as expensive, because you have to write a data page and you have to write an index page. And potentially you have to write multiple index pages if you're using B trees and you've got things being pushed up the tree. All right. No buffering. Yeah. So I did assume some buffering. I assumed that we had the header page already buffered. But if we hadn't, then all these zeros become 1, where we have to read in the header page, then do everything we were talking about, and then write the header page back out. All right. Merge sort. All right. So if you've looked at the sorting video, and you should have, you would have seen that the way databases work, as far as sorting goes, they don't use any of these in-memory sorts like quicksort, bubble sort, selection sort, whatever. They're not appropriate, and they certainly don't work in the context of large amounts of data. So you can't do a quicksort on a file where you've got multiple data pages. Well, in theory you could, but it's going to be quite expensive, right? So the way databases deal with sorting is merge sort, and not just two-way merge sort like you probably would have seen in your data structures courses, but n-way merge sort. All right, so let's have a look. So we've got a data file, which I think I can push over here, which has, I can't push it far enough. Oh, well. Ooh, that's unfortunate. Where's it gone? Oh, I'm in the wrong directory. If I go pop D. Oh. I think I might have the answers out of order with questions. Yeah. Oh, I'm already there. Cool. All right. So let's see. Yeah. All right, so we got that many tuples. Notice that we've got fixed size tuples. So every tuple in this table is 62 bytes long. Pages, 4K long. Each page has a header, which might contain things like pointers to overflow pages. Might contain the counter of the number of tuples in the page. Could contain free list pointers. But in any case, there's 96, and obviously you can see I've engineered that so that that works a little bit nicer. And the other thing that we have, now remember here we're dealing with fixed size tuples, so you don't need to manage free space. The space is divided into fixed size slots, and all you need to know is whether a slot is occupied or not, and you can do that via a single bit, which we call a presence bit. Okay. All right, so got to work out number of tuples per page. So we've got R tuples per page. We're trying to work out C, and so C has to make sure this property is satisfied. So that's the total size of the page minus the size of the header minus the length of the presence bit array. Now this was an unfortunate. Oh, that's, yeah. Right, so D is actually a measure in terms of bytes, not in terms of the number of bits, which is kind of what it sounds like there. All right, so we've got the page, total page size, minus the header, minus the directory, and that's the amount of data space that we've got in the page. So that amount of data space can contain C tuples that are all of length 62 in this case. All right, so if we work through it, we end up with a capacity of 64. Now that wastes some space because we've still got 24 bytes of unused space. How did I come up with 64? I'm no good at solving these kind of things, so I had a guess, and maybe I started with 60. That was clearly too small. Tried 70. That was clearly too large, and ended up at 64. All right, so that's the total amount of data space, total number of bytes that we're using for data. This is the total amount of space that's left or total amount of space that's available for data once we take away the space for the header and the space for the directory. So there are that many bytes. Fortunately, that's larger than that, and so that many bytes will fit. Could C be 65? Well, no, it can't, because even though there are 24 bytes of free space, that's not going to be big enough to hold one more tuple. Right, so we end up wasting 24 bytes of space in the directory, in the page. Okay, well, given that C is equal to 64, now it's easy enough to work out the number of pages. So it's just the ceiling of that. So 16K pages. All right, now, so we've got 16K pages. All the pages are full, and they remain full while we're doing the sort. Hopefully that's true. I think, yeah, it should be that they're all full. All right, so imagine we got 9 buffers, and we've got 9 buffers that can all be used as input buffers, or we could have 8 input buffers and a single output buffer. All right, now I might try and go back to the sorting slides just to have a look at the scenario. Oh. All right, I'll have to, here it is. Okay, so in the initial pass, we use all of the buffers, and what we do is we read B pages into the buffers, and we do an in-memory sort. Now, since everything's in memory, yes, we can use things like quicksort and so on. They'll be a little bit different to the normal quicksort because these aren't single elements, but I guess if you really wanted to, you could copy all of the tuples into a single array and use quicksort to sort them. Either way, we're doing it in memory, so we can do it relatively quickly. So we can sort a chunk of B data pages. So that whole chunk is sorted. All of the tuples in here are less than the tuples in here, dot, 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 or less than the tuples in here are less than the tuples in here. And then we can write all of those pages out to an output file, which is not totally sorted, but it has all of these runs of B pages that are actually sorted. All right, so the way in-way merge sort works is that we then have passes that take n of those sorted runs and do a merge on them. So here you can see we've got n input buffers, and we'd read the first page of the first run into here, first page of the second run into here, first page of the third run, da, 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 first page of the the nth run into here, and start doing a merge. And we gradually consume those runs of length B through these input buffers. And when we're doing the merge, we simply find the smallest value in any of these buffers and we stick it in the output buffer and then advance the next tuple pointer in that buffer. And as soon as this fills up, we write it to output. So when we're filling up this output buffer the first time, we're getting the smallest values from each of these runs, and we're going to put the 64 smallest tuples into here and then write that out. And then as we continue with the merging, we'll put the next 64 smallest tuples into here, write that out. So clearly what we're going to end up with is a sorted run which is n times as large as the original sorted runs, which were of length B. Right, so B times E. Okay, so let's go back and start analysing. Right, so first pass, 9 buffers. Here we don't need an output buffer because we're filling up 9 buffers, sorting them internally, and then writing them out one after the other. So the input buffers effectively act also as output buffers. All right, and then for the subsequent passes, we've got 8 input buffers and 1 output buffer. So clearly we're doing an 8-way merge after the first pass. All right, so how many runs do we end up with after the first pass? We end up with 1,800. So 16K total number of pages, length of each run in number of pages. That's the number of runs that we end up with. All right, so how long are these sorted runs? And basically a sorted run is a sequence of pages where all of the tuples are sorted. So all of the tuples in the first page are less than all of the tuples in the second page, and so on. Right, so after the first pass, we've got runs of length 9. After the second pass, we take these runs of length 9 and we merge 8 of them together, and that gives us a single run of length 72. And then we repeat that. We take these runs of length 72, we merge 8 of them together. That gives us runs of length 576. We then 8-way merge them to get runs that size, and then we 8-way merge them again to give, well, once we've done that, we've clearly sorted the whole file. All right, so what we're interested in working out here is how many times do we have to pass over the input. And so that we've got 1 pass for the initial sort. Notice that each time we do this, we read the entire data file and we write the entire data file. So every pass corresponds to read the file, write the file. Now you're doing it obviously doing it using merging and so on, but overall the cost is read all the pages, write them all out. So we've got the initial sorting pass, then we've got 4 passes that are doing merging, total of 5 passes. The total file size 2 to the 14. On each of these 5 passes, we read the entire file and we write the entire file. So it's essentially 2 times the size of the file in terms of pages. And then we do that 5 times. So that was only allowing ourselves 9 buffers. What if we crank it up a bit and allow ourselves 33 buffers? All right, so after the first pass, we'll end up with 497 runs, each run of length 33. Hope that's right. It doesn't look quite. Let's see. What was it? 33 times 30. 497. Okay, all right. So it's more than 16K. So 497 runs of length 33. All right, so that's what we've got after pass 0. The sorted runs are of length 33 pages. All right, so we've got 33 buffers, so we can use 30, we can do a 32-way merge, 32 buffers plus 1 output, 32 input buffers plus 1 output buffer. No, 2 to the 14 is the total number of pages in the file, which we worked out way back up here somewhere. Yeah, here. Okay, so there are 16K pages in the file. All right. So where are we? Yeah, we're up to here. So we do a 32-way merge. After the first pass, we have runs, sorted runs of length 1056. So the whole file's not sorted unless the length of the runs is greater than the size of the file. And clearly, after we do this pass, and by the way, I should have said that not all of these runs are going to contain 1056 pages. So we're going to possibly, unless, everything's a power of 2, we're going to have one run at the end that's shorter than all of the others. But that's fine. That all comes out in the merging. It's not an issue in any way. All right, the next pass, we end up sorting the whole file. So now we've only got 2 merging passes rather than 4. So that's the cost. So if we go back up here, we had 5 passes. Now we've got 3 passes. By increasing the number of buffers by what you could say is a modest amount. All right, let's crank it up even more. Let's take 257 page buffers. So obviously after the first pass, we're going to have runs of length 257, and we're going to have 64 of these runs. Like I said, the last run might be not length 257, it might be length 200 or something like that, but doesn't matter. All right, so that's the length of runs after the first pass. What we're then going to do is a 256-way merge, and that's going to sort the entire file. So we've only got 1 merging pass, we've got 1 initial sorting pass. So the overall cost is read and write the file twice, which is less than that, a bit less than that, but we're using substantially more memory, but it's way less than the first one, where we only had 9 buffers. So pretty much the more buffers you can throw at it, the better. 256 doesn't sound like an excessive number of buffers compared to the total number of buffers that Postgres would have available. Of course, it's got to share those buffers amongst all of the backends that happen to be hammering the database at the time. Yeah, right, so that's not huge. All right. So n-way merge sort is a useful strategy to sort very large data. And I should point out, if you look at the Unix sort utility, I'm pretty sure that does a merge sort. And it puts its intermediate results in /temp. So if you do sort on a very large file and then go and look at /temp while the sort is running, you'll find a bunch of files that are connected to the sort operation. Right, so you can sort arbitrarily large amounts of data using this strategy. Even if you've got a relatively modest number of buffers, that doesn't matter. It just means it's going to take more passes to find. Thanks, Curtis. Okay. Right, and what is it? It's 1:45. Almost tempted. Yes. You must have very small workloads then, that's all I can say. Oh, why am I looking at that? Not database scale workloads. All right, here's another cost analysis. Maybe I can quickly take a look at that. I think this was copy cost, yeah. All right. Let's see. Probably I need smaller pages to be able to do this sensibly. Doesn't matter. And let's forget about the file header for the time being. Right. Don't have a hash. Don't have them. Right, so we're simply doing a copy data to data. So how to do that? Pretty straightforward. If this is the input file and output file. All right, so initially this file's empty, and we could take page of data, copy it to the output file. Page of data, copy it to the output file. That would be that'd be the obvious way to do it. However, if there are gaps in some of these data pages, i.e. tuples that have been deleted, we might actually be able to make this file a little bit smaller by filling those gaps as we copy. What does copy minus L do? All right, fine. So the number of pages in the output file could be smaller than the number of pages in the input file if there are gaps in the data pages here. That would make the copying marginally more complex. It's not just a matter, read the data page, write the data page. It's, in fact, read the data page, get an empty output page, and then iterate through the tuples and insert each of those tuples into the data page, into the output data page. If you haven't filled that up, then you'd read that, well, even if you have filled it up, if you have filled it up, you'd write it out. And then the output data page would look a little bit similar to the input data page. But if this page was only half full, the output data page would only be half full at this stage as well. So you read the next input data page and scan through the tuples, copy them into this output page, and when it fills up, you write it to the output file. And you can keep doing that. And so you might eventually end up with a more compact version of the in file in the output file. So this is basically what this is saying, that it's possible that B out is smaller than B in. It's obviously never going to be larger than the input file, but could be smaller. Oh. Yeah. So we could have that. Oh no, I meant to save the file from before. Oh well, too bad. The only way I'll ever see these pictures is on the screen in the video now. I suppose I could go back and do screenshots, but I'm not going to. That would take too long. All right. If we've got, so yeah, these files are both heap files, so there was no ordering of the tuples, so whatever, we could just stack tuples in here till it was full, write it out, stack more, and so on. Right, if we got a sorted file and we're writing it to a heap file, then it's pretty much going to be the same. If the sorted file involves overflow change, sure, you'd read this page and then, in fact, this is interesting. So heaps aren't inherently sorted. So one thing you could do, you could just read through the input file and write all the pages out, and then you could read through the overflow file and add those pages on the end of the heap file. Now you would have totally lost your ordering. If you thought it was important then to preserve some semblance of ordering, then you could read the data page, write the data to output, read the next data page, write them to output. If there are overflow chains, read through the overflow chains and copy all their data to output. So there would be a little bit of ordering there. But as I said before, even a sorted file, the data doesn't have to be ordered within the page. All that you really need to know as far as searching and so on goes is what's the smallest key value in the page and what's the largest key value in the page. All right, so yeah, so scanning through a sorted file, whether it's got overflow pages or not, is copy once it's a single scan through the data file, and then if you like, a single scan through the overflow file. So the overflow file is going to be a separate file to the primary data file. All right, what if we're starting from an unordered file, a heap, and by the way, I should have said, I didn't say it before, I probably said it somewhere, this is not the same as a heap data structure that you see in your data structures courses. Basically, it's just a heap of junk. So there's a whole bunch of tuples in one page, a bunch of tuples in the next page, and so on. So Postgres calls it a heap of tuples, I guess. All right, so if we're going from a heap file with no ordering at all, and at the end we want to produce a sorted file, then there are two strategies. One, you could try and maintain the order on each insert, remembering that the input file has no order at all. So you read the input file, and for each tuple in the input file, you effectively insert it into the output file. So however much it costs to do an insert into the into a sorted file that we talked about before, that's the cost that we're dealing with there. And that's how many times we have to do it, because we have to do it for every tuple in the input. And where's that? In other words, we've got to do this for each input n tuples, each input tuple, not tuples, no, for each input tuple. What am overloaded, what? An overloaded term in computer science. I don't understand, Curtis, you'll have to explain. Oh, you're doing heap. Yes. All right. What else is it used for? Priority queues, this, any other thing that it's used for? Can't think of one off the top of my head. All right. In any case, so that's one strategy. Oh, yeah, okay. Yeah. Right. Gotcha. Yes, every piece of jargon in computer science is overloaded, so we don't have to think of any new words. Could have called it a pile, I suppose, although that's not quite, doesn't quite capture it. That captures the notion that things are piled up on top of each other. All right, so the other strategy that we could use here, we could read the input file, we could make an output file, and then we could sort it using the method that we just described. So which of these is going to be cheaper? I'll let you work it out because it's time. I mean, think about it for next time, next week. Except I'll probably be talking about something else like projection. Okay, that's enough for today. Now I've got to try and stop this Zoom thing, stop recording, close everything up. So stop sharing. And, oh, what? Why do we need to be out? Oh, okay, hang on. Oh, all right. So this is the original copy, and Yeah, good point. In fact, I don't think we do. Because, yeah, all right, this actually produces a sorted output file. Thank you. Good question. Yeah, but I mean, the cost of writing the output in the sorted case is kind of taken account of in this cost formula. So this is the cost of the base copy, just copying one heap to another. So it should look the same as that. And I'm not screen sharing, so I don't know why I'm pointing. All right. Yeah. So that second B out isn't necessary because it's covered by in the cost of the sorting the file. All right, enough raving. That'll do. I'll quit and wait for the recording to be